Welcome to the CEAT Research Seminar Series, Virtual Edition.
He is the recipient of the NSF Career Award in 2020 for his work in the area of distributed optimization in complex multi-agent networks. His teaching has been recognized as well through the 2020 CEAT Excellent Teacher Award here at OSU. The title of his talk is Bi-Level Distributed Optimization in Directed Networks. Farzad, take it away.
Thank you so much, Dr. Bunting. I want to thank the CEAT organizer, the organizer of the seminar, Dr. Bunting, and his staff for their great effort and initiating this very informative event. It's a pleasure to be presenting in this seminar series. So I'm going to share my slides. Can everyone see the screen? Okay, great. So just quickly maximizing this. Okay. All right. The talk is about bi-level distributed optimization in directed networks. The idea of distributed optimization in networks overall has been around for years and has been advanced actually throughout the past few decades. And one reason is the trending topic or applications in the area of big data and sensor networks. Today, I'm going to focus on the bi-level format or formulation of these problems, which has been the focus of my research in the past few years. And so first, let me just give you a little bit background about the NSF project that has been recently funded. So this research is basically part of this bigger project, which focuses on multiple agents that communicate over a network to cooperate to minimize a global objective. So simply the math model can be represented by this formulation. But there is more into this because the communication rules have not shown in this math model. So you can see those more in details in the algorithm side. And the goal so this is the classical model, and the goal of this project is to advance this math model and try to capture more complex problems in real world. And those the applications arise in different areas. One is distributed remote sensing, and then second is renewable energy and in power systems. And third is the efficiency estimation in networks, in, let's say, transportation networks. These are the overall or broad application or avenues for my research. And so
let me, pardon me, I hate to interrupt. Your slides are not advancing. I'm not sure if that's your intent. Okay,
okay, so do you see the acknowledgement?
Yes. Yes.
Okay. What if I just maximize this, because I wanted to maximize the screen. If I go now to this slide, do you see the slide 3?
No.
Oh, okay. Sorry. So I need to then just work with this page then, because then I maximize. Okay, sorry. Yeah, I'm just gonna have it not maximized. Okay. Yeah, as I was just talking, this SOL that you see here represents the solution of what is called a variational inequality that is an immensely powerful tool to capture complex constraints and complex models. And one example is the equilibrium in Nash games, for example. So using this more advanced math model, we can capture more or broader applications. So specifically, I'm going to first start with a few motivation or application areas that why distributed optimization has been, very popular in these regimes in a standard network. So I'll give 2 examples of standard networks, and then I'll talk about complex networks. This is the area of distributed and parallel image restoration, where you have a minimization problem. We have a summation of least 2 norm squared of a linear term like this. And basically, the idea is that we are given an image, a blurred image or noisy image, and then image can be decomposed to among different computers that can communicate with each other over a network. And the goal is to reach to the optimal solution of this problem, which actually is a de-blurred image. And so the communication happens over a network that can be designed effectively. And as you can see, these little blocks, they appear to be a more, a complete picture at the end, and then we can recover the original picture. And another area of application is distributed and parallel learning, classification, clustering, regression, where we have an optimization model like this. Again, there's a cooperation among M agents. Each agent has access to a portion of a training data set denoted by SI, and you have a loss function. We have a function called H that, let's say, in deep learning represents the hidden layers, versus in regression is just the inner product of UL and X. UL and VL, by the way, they are input and output of the data set. And so this is basically a classical model, but distributed optimization allows us to store the huge data over multiple machines and boost the computational power and preserve the privacy of the data. And this is in particular important in healthcare applications where data providers are committed to preserve the data privacy. And so the choices for this function L, as you may all know, you can have logistic regression, S-linear, SVM, and more advanced models like deep learning. The next slide, so these were two standard applications of distributed optimization. There was no need to consider a complex model, but thanks to the advancement of the sensor technologies, sensors now are capable of observing and sensing and monitoring large areas of surface, and for example, to detect wildfires in California. And so there are, in this particular application I'm talking about, there are two types of sensors, hyperspectral sensors and multi-spectral sensors. Hyperspectral sensors can capture the spatial and also high spectral information of the images, but their resolution in the spatial is less than the spectral dimension. And the MSI sensors are the opposite of that. The idea here is to combine these two pictures, these two MSI and HSI pictures, to be able to recover a fully high spatial, high spectral image, as you can see here. And this model has been studied before. It can be captured by this optimization model, which is a convex formulation. But in real-time application, there is a need to tune the regularization parameter throughout the model, and regularization is used to deal with ill-posedness in these models. And so recently, bi-level formulations to address ill-posedness have been considered. And as you can see here, we have a summation of functions in the objective level, and in the constraint level, we have more complexity involved. And this is one application of the research I introduced in the beginning. And the second application in complex networks is, of course, with the increasing penetration of renewable energy, there is a need to advance the optimization algorithms, because optimization problems appear in many levels in power system and power market problems, in commitment level, in dispatch level, and also planning level, and also in expansion levels. And the one I'm showing here is a two-stage stochastic programming problem that can be used for stochastic unit commitment problems in general. And so basically, this two-stage stochastic problem can be reformulated excuse me, as a bi-level problem, as you can see. And again, we have a summation of objective functions that can be seen as the local functions of objectives corresponding to agents. And then we have another level of optimization in the constraint set, which brings complexity into the model. And then the question is now, can we still apply the algorithms in the literature of distributed optimization to be able to solve this large scale problem in a reasonable time. And that's very important because, you know, in real world applications in power systems, scenario-based approaches have been used, and this is because of the uncertainty in the supply level and also in the demand side. Basically, in the demand side, the uncertainty comes from consumption of energy by people, and on the supply side, it comes from the uncertainty of the renewable energy. And for these two reasons, these problems end up with being very, very large, and it's very crucial to be able to you know, boost the computational power of the optimization algorithms by applying the approach of parallel computing, basically. So that's the motivation of why a bi-level formulation is considered in this talk. So let me begin with now the very specific problem formulation in this talk, and maybe I can just make it larger now. Okay. So the problem formulation is a bi-level optimization problem where the objective function is just similar to the classical model, but the constraint level has now another optimization problem involved. And here is the idea. So agents have access only to the information about each Fi and Gi, and they are going to cooperate over a network, communicate with each other, and run an optimization algorithm in parallel, basically, or in a distributed fashion, to cooperatively find the global solution X, which let's call it X star. And so in this particular work, I'm gonna assume the following properties of the functions, convexity and smoothness properties that are standard assumptions in the literature. So before I talk about the outline of the algorithm, let me just briefly talk about the idea of the directed network, because the communication happens over a directed network. So basically, let's just say we have a directed network and denoted by N and E, and N is the set of vertices, and E is set of the ordered pairs. And one thing I'm going to utilize in this talk is the correspondence between a graph for communication and a matrix that can represent that graph, because working with matrices in math is much easier in the algorithm side. And so there is a digraph induced by a given matrix. So if we have a matrix B, we can imagine a digraph induced by that, basically simply by this definition. If there is a Bij greater than 0 in that matrix, there is a connection from node J to node I. That's the idea. And this represents the set of parents of node I. This represents the set of children of node I. And let me just, before I present the outline of the algorithm, I want to just take a few seconds to talk about the idea of the algorithm and the advancement in the algorithm side. So as you saw, the bi-level problem is challenging because we have optimization in both levels. And duality theory, which has been around for many years and has been applied in optimization to relax and contend with constraints, cannot be directly applied. And for that reason, my research has been around finding a solution for that challenge through the idea of iterative regularization, inspired by the contributions of Andrei Tikhonov, a Russian mathematician in 80s. So the interesting thing is that using the idea of iterative regularization, we can establish new constraint relaxation methodology that works this way. The function G that appeared in the lower level can be regularized by the objective function in the upper level, and we can then focus on this function as a unifying metric throughout the method. So I point out to this term in the next slide in the algorithm. So lambda is actually the what's called the regularization parameter. And what's crucial in this research, as I've mentioned here, research question lies in how to update this parameter throughout the algorithm. in order to keep a balance between the two levels of the problem, the function g that appeared in the lower level and function f that appears in the upper level. Of course, this g and f are summation of gi and fi's. And we have this challenge that the agents do not have access to the global information of this function g and f. That's another challenge that needs to be captured in the method. So I'm going to just present this heavy notation and based algorithm, but the idea is pretty simple. The main idea is that if you imagine, let's say, there are different computers solving a large scale problem, at each iteration of this gradient type method, what happens is that each agent I sends some information to the neighbors. And this information includes its belief about the solution, which is xjk, a copy of the global solution, and some approximation of the gradient, which is captured by yjk. And then it pushes information to the, again, the children of it. And so that information is just the approximation of the gradient yik. And so the whole idea here is that x and y can be updated as using a weighted average of the information of the neighbors. And I'm using the idea of iterative regularization here in particular to be able to enable this algorithm address a bi-level problem. The research question lies in finding out update rules for this iteratively updated regularization parameter, and also which is called the step size. There are more detailed assumptions, but time doesn't allow me to go through this, so I'm just going to skip this and show you the main results. The main result is actually as follows. If we update the step size and the regularization parameter by just harmonic step sizes, harmonic rules like this, where there are details about how to update them here, we can actually derive very interesting and new convergence rates for different terms. For consensus, we actually get not an asymptotic convergence, but for consensus violation, for suboptimality, which captures the difference between the global function f and the optimal value of it, that can be characterized. The complexity can be characterized by this bound. So the whole point here is that we can guarantee some speed for this new algorithm to solve now more challenging problems. And so that's one interesting and exciting news. The second, now I'm going to just show you briefly two implications of that result, because the bi-level model I showed you can capture subclasses of problems. And one is that we can have a minimization of fi over some constraints, and so we can still recover if we capture the infeasibility using this function. We can get more, we can get these new convergence rates again. And another class of problems is ill-posed problems that appear in image restoration and image deblurring. We can still get new rate results for all these terms here. I'm going to skip the detail just for the sake of time and move on to the main results, because then I'm going to be able to explain the idea maybe better. Let's just revisit this problem of distributed ill-conditioned linear inverse optimization, where we are given a picture that is blurred, and we are going to decompose it to 9 blocks. And you see these are just little pieces of the picture. And imagine that this information is just the information given to the first computer or first processor, and then the second one, the third one, and 9 of them. And they start running that algorithm, communicating over. Now here, I'm assuming that it's a ring network or cycle graph. And as you see, the picture that each computer shows, it's getting better and better, and approaches to the blurred picture. And after 10,000 iterations of that algorithm, you have you reach to a consensus over the network And the average of, now these pictures can be seen as the optimal solution or approximation of the optimal solution. Okay, I have a video to show you about this process. I'm just gonna run this to see the progress. If this was maximized, this wouldn't show up here, but you can still probably see the progress. So it takes a few seconds to show that the deep learning process is, making progress. And so it's still blurry, but if we give it more time, it's going to recover the original image. So let me just, it's the changes then decay, and this is where it reaches to consensus. But let me just go back and show you again the beginning of the algorithm, because in the beginning, we just start with these local information across these 9, let's say, a screen of monitors of these computers. And then as I go forward through communication, local communication over the ring graph, you see the progress, and the pictures are deblurred. The second application is basically the distributed linear soft margin SVM. There's a classical model, but in this implementation, we are able to do or optimize this formulation in a distributed fashion. So the training data is stored locally in here 10 computers, and in this is showing you how the centralized scheme, the gradient method that needs all the data to be stored in one computer, behaves and performs compared to a distributed one, which is the algorithm I explained. It's a very little difference, and actually I ran it for very few iterations, but if I run it more, you won't be able to see the difference between the distributed implementation versus the centralized implementation. And you can see that the for different topology of the network, star graph, line graph, both feasibility, infeasibility, and optimality metrics, they do pretty well. They go to 0 fast. Okay, just to conclude my talk, we consider distributed optimization over directed networks motivated by application in machine learning, and also sensor net for wireless sensor networks. We introduce a unifying distributed optimization model that can be characterized as a bi-level formulation, and utilizing the idea of regularization and iterative regularization in particular, we develop a new push-pull algorithm, gradient algorithm, that can solve this 2-level or bi-level problem. And we got some nice theoretical results. In addition, we also see we observe that the algorithm performs well in different applications. This is a paper under review in American Control Conference, and this is the preprint of it. I'm gonna, and this is where I'm contributing with my graduate advisees, Harshal and Jayesh, and we are going to work on advancing these ideas through more complicated networks, time-varying graphs, because the one I considered here was just a static graph, non-convex case in deep learning, asynchronous communication. All these are very exciting directions that we can consider. I want to conclude my talk with saying that, first of all, thank you all for your attention. I've recently developed a course on this topic. It's offered next semester. So if you're a faculty and you have graduate advisees who are interested and need to take a course like this, I would be happy to have them in my class. So thank you all. And yeah, I'm happy to take any question if you have time.
We absolutely do have time. Farzad, thank you very much for your talk. We have about 5 minutes for questions and Q&A. I would ask that you please show the video. Go ahead and turn your cameras on if you don't mind. I think we have the bandwidth to handle that, and ask your question. So please go ahead and ask away.
So this is a very nice talk for us. I have a quick question on the benefit of distributed optimization. Some of the literatures indicated there could be linear speed up. I mean, that's for stochastic gradient descent. So I wonder if you see that here, and also uh, what do you think about when one would apply this to large scale machine learning algorithm? When you take, I mean, you cannot process all the samples at the same time. You might just need to take a subset of it and process it. How would that impact the overall performance and convergence? Thank you.
Thank you. That's a great question. And actually, as you mentioned, throughout these years, it's been always an ambition of researchers to recover the same convergence speed for distributed optimization as the ones that centralized optimization has. And so that's always been a challenge. The good news is that in the past 2 years, the idea of gradient tracking was introduced, and using that, algorithms were able to recover linear convergence, even for for this deterministic case. But there are a couple of papers recently published in this area that show a very basically they show a linear convergence for a problem like the one that I showed you. But when it goes to a bi-level formulation, so that's for one level. When it's a bi-level, we lose actually some of the speed. But referring to the application, because the motivation here is not just to address larger scale problems. Even if you have a smaller scale problem, if you want to preserve the privacy among the agents or privacy for the data, and we don't want to reveal, because one fascinating thing about distributed optimization is that throughout the algorithm, the data is not communicated. What is communicated is actually the belief about the solution only, and that allows for preserving the privacy, which is independent from the interest in speeding up the algorithms. But yeah, research has been very active in both of these areas.
Very good. Thank you for that question and that good answer, Farzad. We have time for one more question. I will ask one. What kind of collaborations do you think would be useful as you think about the different folks across the college? I mean, you've given a very compelling talk in a pretty interesting area. Who would be drawn to this?
Actually, that's what I've been always trying to pursue, because the optimization by itself is an interdisciplinary area. As you saw in my talk, there are problems arising in power systems, in machine learning, computer science. So I see a lot of opportunity for collaborating with people in electrical engineering, in working in unit commitment problems, expansion problems, especially the ones that have discrete integer variable or integer variables. Also, researchers in computer science who work on machine learning, deep learning, especially, because that's actually a future direction of my research. So I would be pleased to collaborate with faculty across campus on these directions.
Very good. Thanks. You might visit with Gulian Fan over in electrical and computer engineering. I know he does a good bit with image processing. So I'd commend him to you. So thank you for your talk, and I appreciate it. And
thank you so much.
Others can clap, and you can clap virtually. We appreciate you taking time today to talk, to give the presentation.